Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the 7th chapter of microwave engineering, where the microwave transmission lines we have been addressing so far. We started to address these topics, first of all understanding a circuit model that has involved the lumped elements R, L, G and C corresponding to the per unit length of the transmission line. Now we have been derived by the formulations for reflection coefficient, transmission coefficient, standing wave ratio. Further, we have been using the very popular graphical method called as Smith chart for solving the transmission line problems, and we have extended them to have the single stub and in the previous video the double stub matching technique. So based on the understanding of double stub matching, let us have a problem. So here we are provided a problem statement for double stub matching using the Smith chart. So it starts with the terminating impedance ZL is 100 plus J times 100 ohm and the characteristic impedance Z0 of the line and the stub is 50 ohms. The first stub is placed at 0.40 times lambda away from the load. The spacing between the two stubs is 3/8 of the lambda. Determine the length of the short circuited stubs when the match is achieved. What terminations are formed for matching the line by the double stub device? So this is our problem statement. So from the problem statement, very first of all, we shall determine which are the given details, the given data values. Those can be used further to have the determination of desired values. So at very first of all, we have the value of terminating impedance. The terminating end, that is the load side. So we have the load impedance ZL. The value is provided 100 plus J times 100 ohms. So we have the complex representation, the real part equal to 100 and the imaginary part also equal to 100 here. Now along with this load impedance, we are further continued to another value, that it is the characteristic impedance. So characteristic impedance is denoted by Z suffix 0. Here it was ZL, now we have Z suffix 0 and it is for the transmission line as well as for the stub and the value is 50 ohms. So this is the second and the third data given value we can say. In our one of the previous problem, we had the different values for characteristic impedance for the transmission line and for the stub. But now here we have both the characteristic impedances of transmission line and that of the stub value are equal and the value is 50 ohms. So now we have the three given values ZL, Z0 and Z0 S we can say corresponding to the stub in the subscript. So very first of all, we shall be noting down the given details and we continue with the sentence here. The first stub is placed at 0.40 times lambda away from the load. The spacing between the two stubs is 3/8 lambda here. So these are the another two given values we first of all note here. So we note here the load impedance ZL is equal to 100 plus J times 100 ohm, whereas Z suffix 0 is equal to 50 ohm. Let us say this is characteristic impedance of the transmission line. Z suffix 0S is equal to also 50 ohms characteristic impedance of the stub here. Now the first stub and we have the second stub and the difference here we have that is of 0.40 times lambda between the two here. Next to that, the spacing between the two stubs we have 3/8 times lambda here. So here we have, first of all, load in this particular case, not the second stub. The second stub here we have. So I can write here 3 by 8 times lambda as per the problem statement here. Now what is asked into the problem statement? In the problem statement, we are asked to determine the length of the short circuited stubs. So this is the first requirement to be determined here, and the provided condition is that, of course, the matching is completed here. The single stub matching is to have the load impedance perfectly matched to that of the characteristic impedance, so that the transmission line will be a flat line. It will not produce any kind of reflected wave. Next to that, we have also been asked the information that what are the terminations that are forbidden for matching the transmission line by the double stub device. So forbidden, that means not allowed. So this information also we need to provide to solve this problem at last. So let us continue with step-by-step approach with the help of Smith chart. So now, very first of all, we mention the step number 1. The step number 1 is to have the computation of normalized load impedance. So initially we have been provided capital Z suffix L. Characteristic impedance is also provided to us. Therefore, normalized impedance can be represented as small z suffix L, and it will be the ratio of capital Z suffix L divided by Z suffix 0. So let us substitute the values here. Here it is 100 added with Ga times 100, and it is further divided by 50 ohms, the value of characteristic impedance. So therefore, we obtained the normalized impedance Z suffix L is equal to 100 by 50, it is equal to 2, added with 100 by 50 again, so J times 2 it is. So let us outline the intermediate value. And now we have the normalized load impedance. By the next step, we get the conversion to that of the load admittance here. So for the load admittance, we shall be first of all plotting the SWR circle. SWR is represented by rho symbol here, and we shall be reading the normalized load admittance, and which is 180 degree out of phase from the normalized load impedance small z suffix L, and it is onto the SWR circle here. So onto the Smith chart, we shall be drawing all these details. So this is our Smith chart, and as the value of load impedance here we have, the load impedance is 2 plus J times 2 here. So on this Smith chart, we have 2 plus J times 2. So in the constant R circles, we have R is equal to 2. Whereas into the constant X circles, that is the constant reactance values, we have X is equal to also 2. So on the horizontal axis, we have the several values corresponding to the R here. So we start at 0, then go for 0 0.1, 0 0.2, 0 0.3, 4, 5. This way we have at the center of the Smith chart that it is 1.0, and here we come to have R is equal to 2. So this is the circle R is equal to 2 in the upper half, positive side of imaginary part, and in the negative part, that it is the lower part of the Smith chart here. Now we have positive J2 here. So on this particular circular scale here, we need to find the value of 2 here. So here we have the value of imaginary part to be 2. Here we have 1. So in between we have 1.2, 1.4, 1.6, 1.8, then 2.0. We go for 3, 4, 6, and so on. So this is the intersection of this particular line, the arc we can say, and this particular arc. This is the intersection point here. Now we have to draw the standing wave ratio circle here, SWR circle. So for that purpose, we shall be drawing a circle taking the radius that is from center of the Smith chart to that of this marked point here. So I take the center of the Smith chart here, take this much of distance, and let us draw a circle on the Smith chart here. So this completes the circle here. Now the next thing is to have the normalized load admittance. So on this particular circle we have this particular point marked here. Let us draw a diameter to the circle so that we can have a line segment that is joining this marked point, passing through the radius and intersecting the circle on opposite side here. So here we have this diameter here, and when we represent here, this is the point Z suffix L, normalized load impedance. This is the opposite direction point that is called as Y suffix L. It is the normalized load admittance here. So from the Smith chart, here we shall be writing for the step number 2, we have the normalized load admittance. The real part we come to have 0.25, and the imaginary part, as it is onto the lower half of the Smith chart, we have the negative value. So it is also equal to minus 0.25. So let us outline the normalized load admittance value here. Now by the next step, there will be a step number 3 here. We shall be drawing a spacing circle as mentioned in the problem statement. As per the problem statement, we have the spacing between the two stubs is equal to 3/8 times of the lambda here. So let us draw a spacing circle with respect to this information here. So here we mention the task is to drawing a spacing circle. So for this particular case, when we have a unity circle, the unity circle with respect to the constant conductance, so constant conductance denoted by small g, and for unity circle we have the value of g is equal to 1. We have to make a rotation to this constant unity circle by the length of 3/8 times small l, or the lambda here as per the given problem statement. So the phase angle is to be calculated here. So the phase angle will be of 2 times beta into d. So which can be substituted 2 times beta into 3/8 times lambda, the wavelength here. So now here we come to have the value. So beta is equal to 2 pi divided by lambda. So lambda will get cancelled, and here we shall be left with 2 into 2 pi divided by lambda, 3/8 times lambda. So here we have 4 and it is divisible by 8 here. So we will be left 2 in the denominator. So here we will be having 3 as it is, and lambda will get cut, and here we are left with pi here. So it is 3/2 times pi here. Now we know that pi radians is nothing but 180 degrees. So if you get it, 3/2 into 180 degrees, this is equal to 270 degrees here. Now getting back to the Smith chart here. Here we have the marking of 1.0 at the center of the Smith chart. So right from this place, as we have this particular circle, this will be the g is equal to 1 circle, and by making a rotation of 270 degree, that it means we have to go for the third quadrant on this particular scale. We shall be having such a circle located at this particular place. So it will be having a diameter between 1.0 here and 1.0 here. So this will be the diameter and the center will be somewhere here. So let us draw that one. So here we shall be drawing a spacing circle. So this will be the midpoint of this diameter, and now we shall be drawing it like this. So it will be touching to 1.0 on the downward side here. So here on the Smith chart we shall be providing a nomenclature here. So here we provide the name. This is the spacing circle here. Now we have this original circle with g is equal to 1, the radius value here. So here we shall be having yd, the value on the original circle g is equal to 1 here, whereas we shall be having y11 onto the new spacing circle that will be having a phase value changed by 270 degrees here. Now by the next step we shall be having a movement of the distance 0.40 times lambda as per the problem statement. So inside this particular problem statement we have that the information, the first stub is placed at 0.40 times lambda away from the load here. So in the Smith chart we extend YL right from its particular center to mark a value onto the circular scale here. So we have such a marking, and we come to see here this is 0.45 and this is 0.46. So we have the 4 intermediate markings in between. So it will be 0.452, 0.454, 0.456, and this is 0.458 here. So we obtain 0.458 marked corresponding to that of the YL here. So to look at the position onto the Smith chart here, we come to see here, let us say in the step number 4, that the movement of YL is for a distance of 0.40 times lambda here. The position that we have found to be 0.458 onto the Smith chart, we have to move it up to 0.358 here. So on having the new position here along the SWR circle, that is represented by rho circle here, and it will be having the towards generator side. So we have to find this into the clockwise direction here, and we come to have the value of yd1 to be equal to 0.55 minus j times 1.08. So let us outline this intermediate value. So onto the Smith chart we get the value 0.358 at this particular point, and this is our SWR circle. SWR in the bracket rho circle, we provide the nomenclature here. So while we have the rotation, we can show it in this particular diagram. So this is the center of the Smith chart. We start from this end, that it is 0.458, and we go like this up to this particular point. So on this particular Smith chart here, the difference from the position 0.458 times lambda towards the generator that we have taken the direction, and we have come to this particular point here. So let us represent it with a shift of 0.40 times lambda here. Now on this particular Smith chart, as we have this particular position here that has the intersection with that of the SWR circle, onto the SWR circle here we mark a point, and this point is nothing but y suffix d1 as calculated. So here we have y suffix d1 is equal to 0.55. It is the value of small r, that is the constant resistance circle, and this is the value of small x 1.08, that it is the value of constant reactance circle. As we have this particular point intersecting the SWR circle in the lower half of the Smith chart, we have represented it with the negative sign in between the real and the imaginary part here. Now for the determination of y suffix 11, to be having the normalized load admittance at the stub position 1-1 node, we can say here, we have to make the intersection of the circular line that we obtain at yd1 with that of the spacing circle. So if we see this particular spacing circle, here we have this particular line, the circular line, that it is having the value 0.55. So the 0.55 line, that it is between 0.6 and 0.5 line, is having the intersection on left hand side like this here, and the intersection onto the right hand side here. So for determination of y1 value, we obtained the two possibilities there that we shall be mentioning here. So therefore we mention onto the left hand side value that we have obtained y11 is equal to 0.55 minus, as both the values are onto the lower half of the Smith chart, we have obtained it j times 0.11. Whereas the another value we can denote it by y11 dash here, and it is also having the real part, it is the same 0.55, that is the circular line we have extended onto the both sides to intersect the spacing circle, and this is the another intersection at the imaginary value of minus of j times, we have 1.88. So on this Smith chart, we have the two intersection points here. So on this particular side, we shall be marking here y11, whereas on the right hand side, we shall be marking y11 dash here. Now we know one relation with respect to the admittance at the node and at the stub there. So corresponding to the relation at the node 1-1, we have y11 to be equal to yd1 added with ys1. So here it is the admittance normalized calculated with respect to the position of the stub line here, and this is with respect to the main transmission line. The addition of the two, we get the net admittance at the node 11 here. So this relation gives us the determination of ys1 to be equal to y11 minus yd1. So therefore by the next step we can make the substitutions here. From the Smith chart we have the value 0.55 minus j times 0.11 minus, we have the another bracket that has 0.55 minus j times 1.08. So this results into the value of y suffix s1 to be equal to positive j times 0.97 here. So let us outline this intermediate value here. Now in this similar fashion we can also have the determination of ys1 dash, as we have the y11 dash value onto the Smith chart. So this value can be obtained to the value minus j times 0.80. This value also I outline here. Now to the next step we can have the length of the stub here. So length of it will be for stub 1 and it can be found as L1. So this will be equal to, we have 0.25 added with 0.123 times lambda. So this is equal to 0.373 lambda, whereas L1 dash on the other hand corresponding to this one can be determined as, we have 0.25 minus 0.107 times lambda is equal to 0.143 times lambda. Now just now we have calculated the lengths. So length of stub 1 we have 0.373 times lambda calculated. So 0.25 times lambda we have added 0.123. So as in the previous calculation we have ys1 is equal to positive j 0.97. Let us get it to the Smith chart here. So on to the Smith chart, here we have this is 0.9 and this is 1.0. The markings for the constant reactance circles. So these are the imaginary portions here. So the marking for 0.97 as we are having in the positive half. So onto the upper side we get such a marking for the wavelength towards generator here. Therefore here we can mention 0.123 times lambda. So therefore we have obtained here the L1 value 0.25 plus 0.123 times lambda is equal to 0.373 times lambda. In the similar fashion, we can go for the calculation of L1 dash and we have obtained 0.143 times lambda in this particular case. Now getting back to the problem statement, we have been mentioned in the problem statement that the spacing between two stubs is 3/8 of the lambda. So therefore onto the Smith chart we shall be moving from y11 position proceeding to obtain y suffix d2, the position of the second stub. Also the value of y11 dash will be providing us the value of yd2 dash there. So let us have these values determined onto the Smith chart. So on the Smith chart we shall be having the center of the Smith chart and then the position of the y11 here, and to the unity circle we have at the original position we shall be having the intersection in this particular fashion. So we have the value r is equal to or g is equal to 1 here. So this is the intersection with the unity circle and this is the value we have obtained as yd2 that has been given by y11 while having the intersection in this fashion. So on the Smith chart, this intersection point that we have designated by the symbol y suffix d2 is onto the lower side of the Smith chart. Hence the imaginary part we shall be finding from this marking will be represented by the negative sign here. In the similar fashion we have here y11 dash. So let us get the center of the Smith chart here. The length up to y11 dash should be marked here. And now a circle can be drawn that will intersect the unity circle in this particular fashion, and here it is the intersection we obtain. So this is the unity circle that has the intersection at this particular point. So as this is the unity circle, we have the magnitude in the real part to be 1 here, and this is onto the upper half. So we have the positive marking. So we can see here it is 2.0, this is 3.0. We have the 4 intermediate lines 2.2, 2.4, 2.6, 2.8. So this corresponds to the value of 2.6. So this is the point that we have obtained, that we can write it to be y suffix d2 dash here. So this is having 1 plus we have 2.60 into g here, whereas for yd2 we can write 1 minus the value we shall be having here, that it is 0.61 here. So therefore I mention here the 3/8 times lambda section of the line transforms y11 to yd2 and y11 dash to yd2 dash here along the constant standing wave circle. So therefore we obtain yd2 is equal to 1 minus j times 0.61, whereas we have yd2 dash is equal to 1 plus j times 2.60. So let us outline these values at the intermediate requirement. So as like we had the earlier relation at the node y11, the similar relationship we can also have corresponding to the net admittance given by or the contributed by the main transmission line and that of the stub here. Therefore we can calculate the contribution from the stub 2. So initially we have ys2 obtained and the value we come to have that it is positive j times we have 0.61 here, whereas on the another hand y suffix s2 dash is obtained to the value of minus of j times 2.60. So these are the two values we have obtained here. So the value we can have the marking onto the Smith chart here and will be further giving us the length of stub 2. So the length of the stub 2 for the first positive value we have denoted by L2 and it is obtained as 0.25 added with 0.087 times lambda, which corresponds to the final 0.337 times lambda, whereas the L2 dash that may be obtained by ys2 dash, so we have the representation 0.308 minus 0.25 times lambda calculated, finally obtaining 0.058 times lambda. So let us have it represented onto the Smith chart. So onto the Smith chart, if you want the positive 0.61 value, so here we have the scale here. This is 0.9, it is 1.0, 0.8, 0.7, 0.6, 0.5 here. So this will be the marking 0.61, very close to it. So on this particular axis in between 0.08 to 0.09, so here we have 0.61. So 0.61 we have determined here, and if we have the marking here, we have the value 0.087 corresponding to the value of positive j times 0.61. So therefore we have added this value to that of the 0.25 times lambda here and finally obtained this resultant value corresponding to the length of the stub 2. In the similar fashion, the minus of 2.60 onto the imaginary scale, the constant reactance circles there, we obtained the value of L2 dash is equal to 0.058 times lambda. Now getting back to the problem statement. In the problem statement, we were asked to determine the length of the short circuited stubs when the match is achieved. So this particular portion, now we are successful to determine the corresponding lengths we have represented correspondingly L1 dash, L dash, L1, L2 dash and L2 here. Now the another portion that has been asked in the problem statement is what terminations are forbidden for matching the line by the double stub device there. So let us answer this by our transmission line parameters, those we have represented onto the Smith chart here. Now on the Smith chart we have the position of normalized admittance here YL represented at this particular position, whereas we have y11 and y11 dash at this particular point. So we come to know that a normalized admittance YL that has been located inside the perfectly matched area is cannot be brought to the position of y11 or that of the y11 dash here. So we have the short circuited stub we have, and that we have the spacing circle and the constant conductance circle having the radius g is equal to 2. You can see here this is g is equal to 2 circle. So both are having tangential to each other. So therefore we can say that the area under g is equal to 2 will be the forbidden region for the normalized load admittance for the possibly matching of the loads there. So inside this Smith chart, we shall be showing you the area G is equal to 2 circle here. So it is like the Smith chart. Inside the Smith chart, this will be the center for G is equal to 2 here, and we draw this particular circle highlighted for the visibility like this, the upper half and the lower half here. So here we can show that the shaded portion, if you have like this we can name outside that it is the forbidden region. So this was all about the problem that we had corresponding to the double stub matching technique there. Now this was the unit addressing the microwave transmission line, the analysis we have seen, and the problems we have been addressed so far, the corresponding solutions we have tried to determine with the help of the several techniques those are available. Now, as the conventional one of the type of transmission line is the coaxial transmission line or coaxial cable, we can say here. For the transmission in the practical manner here, in the physical manner, we require certain connectors. So the next topic we shall be addressing the various coaxial connectors, and we shall be concluding this particular chapter. And then we can be starting with the new chapter to see the microwave transmission with the help of single conductor transmission lines. We will address the rectangular waveguides thereupon. So I hope you are enjoying learning with the microwave engineering subject. For more information, you can subscribe to Ekeeda channel. Thank you.